Good afternoon, fancy meat computers. How are everybody? Do? Hello. Yes, having good lectures, hopefully. I just gave you access briefly to my unfiltered consciousness, which is just a string of ones and zeros. Yes. Incidentally, me saying plenty of time to sleep when you're dead is not an encouragement of I'm not trying to encourage suicide in anybody, just so you know. You have so much to live for. Like math! Math like we're going to do today. Okay, so anyway. Number 1. With respect to announcements. Number 1, I actually posted the Teams link this time. Instead of just thinking I did, or like having posted it in a different class, and imagine I posted it in this one as well when I didn't. So here's the Teams link. I've made the Teams page public, so you should be able to just find it if you search for it as well. But there you go. So you can now do your tutorials, which probably will be useful. You never know, though. It's always touchy with tutorials, you know? I also wanted to speak briefly. Just pop you over here. Stop. There. There we go. I wanted to talk briefly about the whole traditional versus formal proof thing. Because that was a bit of a bone of contention towards the end of yesterday's lecture. And I just wanted to lay out the case as it exists, taking into account what you've actually been taught. Please keep in mind that, personally, I never did the comp sci stream. So a lot of these definitions, I'm finding I have, I have the same concepts under different names, and that's what happened in this case. So, pursuant to our lecture yesterday, according to Dr. Farmer's description of traditional versus formal proofs, we are squarely in the traditional camp. I definitely agree with the distinction that he draws between traditional and formal proof. For whatever reason, probably because I'm just a hairy-knuckled engineer, what Dr. Farmer terms formal proof, I have traditionally and perhaps erroneously called formal mathematical proof. Let me just close Slack. Get out of here, Slack. Thank you. The way that I was using the term formal in the previous lecture is, in fact, like what I meant was rigorous, according to that scheme. I am, however, going to hold my position that it is possible to express a formal proof by Dr. Farmer's definition in the syntax of natural language. Mathematics is definitely better suited to it, but I still believe it is possible to use natural language to express the same ideas. Otherwise, it would be impossible for a proof to be spoken, which is obviously possible because we're doing it during this class. So, or, he did it during his class. So, there you go. I never actually checked Piazza to see if there was any follow-up, but I'll do that after class. Anyway, I just want to clear the air on that. So, with respect to this class... Ooh, is this actually running? I am actually running, right? Am I out of sync? Lectureception. That's more like it. Okay, cool. All right, close enough. There we go. So, can you write proofs in the assignment with natural language? Yes. However, we expect the reasoning to be rigorous, and it would be good to throw math in there where appropriate. So, yeah. The take-home of this whole thing is that particularly, because this particularly affects you while you're doing your assignments, the assignments, I'm not expecting you to do formal proof in the Dr. Farmer sense. I'm expecting traditional proof from you. So you need to, as Sam points out, it would not be possible if you used completely formal logic. Yes, like we're not. Yeah, that's basically the issue. So I just wanted to harp on this point just a little bit before we move on. So formal logic is very useful, and formal proof techniques are very, very useful for demonstrating beyond a shadow of a doubt a particular mathematical property pertaining to a system of logic. That's kind of the whole idea. However, once you start there are issues with it. Let me put it to you this way. Formal proof takes a much longer amount of time than traditional proof, and you're much more likely to mess it up. Whereas with traditional proof, you are presenting an argument in the same kind of fashion that you would see in the Halmos book or in the Peirce book. Once you start getting into high enough level descriptions of things and systems, producing formal proofs for everything is not productive. It's it's counterproductive. Even in Dr. Farmer's own slides, the advantages of the traditional style of proof are listed as they're better for communication. And, the purpose that I am the thing I am trying to do is communicate with you. And I am trying to communicate proofs with you, so it would make sense that I would use a traditional proof rather than a formal proof. The other thing is that this book, which is the book I'm basing the course on, uses traditional proofs, so that is the standard to which we are going to hold ourselves in this. You never know how much detail is wanted for traditional proofs. Well, that's the thing, is when it comes to traditional proofs, you kind of enter it in, it's kind of an art form, even with stuff like the textbook, the novice in mathematics is going to expect more to be in the proof than the person writing the textbook, and often a lot of the time, because the textbook writer is oh well, you can just imagine this argument being applied to this case, that case, this case, and that case, and it's the same argument. Just swap this out and you're good. Whereas with a formal proof technique, you would need to actually perform those substitutions and demonstrate you would need to demonstrate the chain of logic for each case individually. So, traditional proof has some advantage. And that's why we're going to use it in this course. The other thing that's it's not as easy to do with a formal proof is know what part of the proof is like useful, interesting, or like stuff you can like base knowledge in. Like the important parts of the proof aren't obvious because everything has an equal level of importance, right? So yes. So we're going to be we're pitching our tent quite firmly in the traditional proofs camp. And, yeah. Like, it's not like we're not going to use logical systems or inference rules or deduction. Not recursion. Induction, deduction. We're going to still use all of these mathematical tools, which are still applicable in formal proof settings. We're just going to, we've got ground to cover, so we need to keep moving on these things, Like if I showed you a formal proof, of the fundamental theorem of arithmetic, like that would take ages, and also, you would need definitions for so many things formally construed, and, just one big basically. I'm not saying that formal proof is not valuable. Formal proof is extremely valuable, but don't underestimate traditional proof either. Traditional proof is how mathematics... Like, there's a reason they call it traditional, right? Is because traditionally, the only proofs were traditional proofs. So, and there is an art form to it, Writing a traditional proof is, it's like half writing a formal proof and half writing an essay, right? And I don't mean you to take that structurally. I mean, like, it's like, well, anyway, perhaps I've talked about it long enough. So, yeah. Yeah, so. Can you write a proof in the calc check style? I suppose so. So long as it still, maintains the same level of rigorous logic and rigorous inquiry. So, let's keep moving, shall we? Add to my order. Ha ha ha. That's a joke. That's a joke! Laugh! I can't hear you laughing! Anyway. So, lexicographic ordering, or dictionary ordering, is a way of generalizing an ordering to pairs or even longer sequences of elements. So you may ask yourself, how would one, for example, go about ordering a relation, right? Which is a set of pairs, right? The answer is lexicographic ordering. So if you know what dictionary... Thank you. Thank you for laughing. Thank you, everybody, for your sarcastic laughter. I can tell it's sarcastic. I can tell. So. So, with dictionary ordering, if you have two pairs, mn and m prime n prime, you can establish a ordering relation over them if m is less than m prime, or m is equal to m prime and n is less than or equal to n prime. So, basically, the way that you go through it is you start with the first element, you compare them. If they're not equal, right, if they're not equal, if there is defined an ordering relation between them, you go with that ordering relation. If there is either not an ordering relation defined over them or they're equal to each other, you go to the next element and then look for the same thing. This is how letters in the dictionary, the words in the dictionary are ordered. That's why it's called lexicographic. If you take the set of English letters and alphabetical order as an ordering over them, lexicographic ordering is the way that words are arranged in the dictionary, hence dictionary ordering. So, incidentally, quick quiz for the class. Is alphabetical order over the standard set of English letters, is that a pre-order, a partial order, or a total order? So, of course, now that we have a lexicographic ordering, we can have lexicographic induction, because if we have an ordering, then we can use induction. So, suppose P is a predicate on pairs of natural numbers, and our ordering relation is a lexicographic ordering relation. We take it as axiomatic that if you have P at 0, 0, and for each pair m, n of natural numbers, I guess, given P prime n prime for all P prime n prime less than P what am I saying? Given P of the tuple m prime n prime for all m prime n prime less than mn, we can conclude Pmn, then Pmn holds for all m and n in the natural numbers. Yes, it's total. Thank you. Yeah. There you go. And thank you, Moonstar, for that very descriptive description. This is also known as nested or inner induction. This method can easily be expanded to larger tuples. So, insofar as the lexicographic ordering can be applied to something of, n tuples, like an n tuple, you can also apply lexicographic induction to those larger tuples as well. Induction on pairs is fairly common. Triples are occasionally useful, and we get increasingly rare beyond that. So, there you go. So now let's talk structural induction. I know we've done like 5 different varieties of induction. Wait, did we do 5? Ordinary, complete, lexicographic, and structural. Okay, so 4. We are going to do some more different types of induction as we get into topic 3. So, principle of structural induction. One form of induction we will use frequently in this course is structural induction. Suppose P is a predicate on the members of a recursively defined structure, such as nodes in a tree. We take as axiomatic that for each member S, if from P of R holding for all immediate submembers R of S, we may conclude P of S, then we may conclude P of S holding for all members of the structure. How is this different from regular induction? It's different in that it has like a branched shape, right? So when think about a tree, right? Like, not completely coincidentally related to one of your assignment problems. If you have a predicate that holds for each child node in a tree, or each child node in a like a heap or something, then and from that fact you can conclude that it must also hold for the parent node or the root node, then you can conclude that it holds all the way down. So that's, you might have to also throw in some base cases, but that's, yeah, it is not fundamentally different from, like, normal induction. It's not fundamentally different from it. But it's still important to understand, like if I just did structural induction in front of you and, like, didn't explain it, then I imagine you'd be mad at me. So, here's an example involving beverages. To demonstrate structural induction, let's argue that a teacup contains tea and not coffee. Let's assume that we start off with n cups of tea. Let's also assume that a cup of tea is formed by pouring 2 other cups of tea together to form a larger one. Our predicate in this case is, the cup contains tea and not coffee. Since coffee cannot be produced by any tea combining process, we can conclude that, no matter where we are in the tea pouring process, or which combination of pours or cups we have used, there is no cup which contains coffee. So this is a little bit more loose than I would expect during an assignment. I would expect more math, but, you know, this is kind of like a conceptual thing, right? It's like, imagine you have 2 teacups, right? And you're creating a third teacup from those teacups. You create the third teacup by pouring the tea from the 2 teacups into the new one, and then you have the new teacup, right? If the 2 that you started off with, this contains tea, and that contains tea, and you can make the argument, which I believe you can, that you do not turn tea into coffee by pouring it into another cup, you may conclude that the cup that you produced contains tea and not coffee. And if you know that every teacup that you started off with contained tea and none of them contained coffee, you may conclude that even if you were to pour all of them into one cup through a series of pours, there would be no coffee at the end of it. Yeah. Yeah, so if this refers to lexicographic induction, yeah, it's, again, similar argument. It's not fundamentally different from regular induction. It's just in regular induction if, like with this new type of ordering that we've come up with. Basically, like, the process of induction is very highly dependent on the type of the ordering that you're using. So, like, if we discover a new way to order things, you know, and we will often find new ways to order things because you can perform induction over the depth of a tree or the number of nodes in a tree. You don't necessarily have to do it structurally. Like, coming up in the lecture slides, we have types of induction that we will talk about with respect to the size and depth of abstract syntax trees and not just their structure. So yeah. So it's just that you're inducing or inductioning over a pair, like a tuple, instead of a regular thing. Yeah, it's not that bad. Yes. So. Yeah, so that's topic 2. Last slide comic time. This time it's jokes at the student's expense time. You would not believe the number of instances of this that I get, particularly in first-year courses. So yeah, anyway. So, if you want to read that, you can just pause the video. So let's move right along, shall we? We're going to talk about expressions. Syntax and untyped arithmetic expressions. There we go. I guess before we move on, are there any questions about the foregoing material? I'll take that as a no. All right. So, untyped arithmetic expressions and syntax. So, in order to talk more rigorously about programming languages, we need to learn the languages of formal... Ha-ha! Thumbs up. We need to learn the languages of formal language description. To do this, we are going to discuss a very small, almost trivial language of numbers and booleans, untyped arithmetic expressions, which shall be abbreviated as UAE. Not United Arab Emirates. It's untyped arithmetic expressions. This is not a geography class. We will use formal mathematical tools, although, you know, the degree to which the term formal means formal in the Dr. Farmer sense is, perhaps that should read rigorous mathematical tools to reason about abstract syntax, evaluation, and modeling of runtime errors. We're going to take the evaluation and modeling stuff and put it in topic 4, though. For the purposes of this lecture, we're going to be talking about syntax. Primarily syntax. So, this is probably review. Hopefully this is review, but basic nomenclature, all right? The following nomenclature will be essential going forward. We will describe these informally now and more formally when they come up throughout the course. So, literals, identifiers, expressions, and statements. Literals are values, as we're going to define them later. Examples are like 4 or 9 or true or 82.4, things that are like things that have concrete value inside of your memory system, even though we're largely not really going to be talking about memory systems just yet, or perhaps at all. Identifiers are things we assign names to in our code. So function names, variable names, object names, things of that nature. Expressions are literals and identifiers plus an assortment of operators. So if you take literals, identifiers, and operators, you get expressions. And statements are imperative commands like if statements, loops, assignment statements, return statements, etc. All of these things are terms, but terms can be other things as well. So a term is anything that is in the language, right? So if you have a Python program, that entire program is a term. Each statement in it is a term. Each literal in it is a term. Every operator in it is a term. Or, like, the expressions that are formed by the literals and the operator, that's a term. So term is like our catch-all phrase for syntactic object when it comes to programming languages. So, in order to get into it, we're going to first study extended Backus-Naur form. I'm just going to do a quick poll, see if anybody's heard of this stuff before. It's interesting to me. Have you heard of eBNF before? So, assignment statements are statements, not expressions. You can, like, some exotic languages are going to have assignment expressions, but, there's, in theory, you could have an assignment expression, but generally speaking, assignments are going to be considered statements because we're going to try not to depart too far in our minds from the imperative paradigm. So, yes. So, a few people have heard of eBNF. Oh, okay. Well, eBNF is the extended version of BNF. So if you've done BNF, this will be hopefully primarily review, but Still good to know because we're going to be, using it. You touched on BNF. Okay. All right. Well, let's give it a slightly more thorough treatment. Did you ever have to do an assignment where you had to produce something, like produce a BNF grammar? Or probably not, eh? It's going to be downright essential for this class. So only something like the walrus operator would be an expression and an assignment. Yes. Yeah. Expressions evaluate to some value. Yes, that's a good way to put it. So, eBNF. In order to define a language, we must have a way to define the grammar of that language. eBNF is a standardized notation that computer scientists use to define languages. The concept is somewhat similar to regular expressions. In eBNF, we create rules which define valid grammatical constructions. These rules may be nested inside of each other and may be recursive. Okay. Good. Good. All right. So this is I don't know the degree to which Dr. Farmer covered BNF in his course, but the additions made by the E, a lot of them I'm not actually even covering because we can kind of get by with a minimal set of them. Yeah. Cool. Anyway. So, the following grammar describes how we write the integers, right? So, an integer is defined as a negative sign, optional, a digit, and a series of 0 or more digits. So, here we have two rules. The top level, and a digit is either 0 or 1 or 2 or 3 or 4, etc. So, the top level rule, integer, we have two rules, integer and digit, sure. The vertical bar character denotes a set of options. For example, digit can be any of the numbers indicated but no others. Square braces denote something which is optional. For example, the negative sign, which denotes a negative integer, may be absent because the integer may not be negative. And the curly braces denote 0 or more repetitions of the first contents. For example, 0 or more digits may follow the first. So this is why I'm saying it's a little bit like regular expressions. Like if you take this type of thing and you if you remove the tags and replace it with the actual characters, you basically have regular expressions. So I'm assuming you guys have done regular expressions, right? It's kind of interesting. I've seen languages which actually use regular expressions for parsing of programs, which is kind of interesting to me. I think they're not as easy to work with as something that would be based on BNF or eBNF grammar, but you can get Haskell to do this using the Parsec library. So, although writing parsers is something you'll cover in 3TB3, we're not going to write parsers here, but we do need to understand how to specify grammar. Good, you guys have done regular expressions. Excellent. So get your regular expressions brain in. The following grammar is for writing hexadecimal integers. So you'll notice that hexadecimal integers are basically the same as or as regular integers. We've just added A, B, C, D, E, and F. Now, I know that it doesn't make much sense to have negative hexadecimal. At least, this is not the hexadecimal that you're used to, but it exists because I have defined it, right? It's like I have defined the form of for a hexadecimal integer, All that remains now is to provide some kind of mapping from that to, some kind of semantic. Note that the grammar describing decimal integers is a subset of the grammar of hexadecimal integers. So every decimal integer is a valid hexadecimal integer, right? What's different about them is the semantics. Yes, although every integer is also a hex integer, this does not imply anything about how either group would be interpreted. eBNF syntax describes syntax, not semantics, right? Good. So, here are a few other death in syntaxes. Here are some more examples. For a Python list, items in quotes are taken literally. You can, so this is actually done in regular BNF because it's not using the extended operators. But, if you have a list, you open with square braces. You know that those are to be taken literally because they're in quotes. If they weren't in quotes, then it would mean the optional bracket in the same way as was expressed in the previous slides. And the object list in the middle is an object, comma, object list, or just a single object. Or, I guess, technically in this one, it could also be blank. Yes. So, the point of this example is to show off how these definitions can be recursive, right? So, if you take this object list and, kind of similarly to how you would do a recursion and a tail recursion in Haskell, you can specify the head and then say that the rest of it is a list. And if there's no comma, then that's the last element. Yeah, I should have that in square braces, though, because that should be optional. But anyway, so a Python function, we have a function is the def keyword integer, round braces argument list, colon, new line tab, statement list. Sometimes, if the new lines and the tabs are important, you'll want to, put them in that manner. But yeah. So good. So am I to take it that you guys already have a reasonable understanding and a reasonable understanding of Bacchus-Naur form? Hopefully. How is object defined? Well, see, that's the thing, is to define the grammar for Python objects would take pages and pages and pages because it's a large amount of things, right? It's everything from variable names to literals to, objects which are instances of classes to, lots and lots of things can be aggregated into Python lists because they operate on objects, which is the general thing, right? So yeah, I'm not going to go to the trouble of defining every object that exists in Python, although I'm sure you could probably find it if you looked it up. Let me see here for a second. Python eBNF grammar. Full grammar specification. Haha! There you go. So, if you want the full grammatical specification of the Python language, all you have to do is look at the Python documentation. So yeah. Ta-da! Yeah, /t is tab, yes. Okay, good. Okay. Good. So, it's good that you've seen it a couple of times now because we're actually going to need to use it. Yeah. Yeah, object is an instance of a class. The normal definition. So, let's talk now about our untyped arithmetic expression language. So we will get as far as we can get on the following 7 terms, right? So we have a truth value, a false value, a 0 value, if then else, successor, predecessor, and is 0, which is a predicate. A predicate on non-Boolean values, shall we say. So, here, T is a meta-variable. eBNF is a meta-language, not metal-language, but meta-language, a language which describes languages, and T is a variable of that language. So, this is very small. I realize this is very small. And you'll notice the distinct absence of anything resembling state, right? We're not concerned yet about variables. We're not concerned yet about memory interactions, really. We're not concerned about loops. We're not concerned about functions. We're not concerned about classes. We're not concerned about structures. There's a lot that we're not concerned about right here. But this will be a sufficient description for us to explore the mechanisms of describing semantics and syntax. So, semantic observations. You may have noticed that we are defining the natural numbers in terms of a zero and a successor function, similar to piano arithmetic. For convenience, we will sometimes abbreviate successive applications of successor using Arabic numerals. For example, the successor function applied 3 times is 3. We will use a number of beta variables, such as s, t, u, and v, throughout the course, in the same way that we might use n and m for the natural numbers. What is the difference between extended BNF and regular BNF? Basically, it adds in a bunch of the stuff that you use in regular expressions to make your life easier, like repetition. You don't necessarily need to define things as like recursive if you use the curly braces sometimes. There's like a whole bunch that I sort of glossed over as well. eBNF. So, yes. Yes. Yeah, so you can see, yeah. I don't know, people like to add more stuff into it as time goes on. It's just like, it's BNF with an extended symbol set. That's it. It's just, you know, in the same way that, like, if you do regex, like regular regex versus extended regex when you're doing grep searching, it's, you know, it's a similar idea. Anywho, you may notice as well that we have a very minimal number of operations. Why are you even there? There we go. Sorry. You may notice as well that we have a very minimal number of operations on our 3 literals, true, false, and 0. We have only a conditional, a predicate testing if a term is equivalent to 0, a successor, and a predecessor function. And technically, we don't need the predecessor function. We compose our terms in our language using our recursive grammar. So, this is how you would compose terms in this language. If false, then 0, else 1, this would evaluate to 1. Is 0, predicate or predecessor successor of 0, is true. We will use the double angle to denote values resulting from execution of small programs in our small languages. For ease of use, we will often use round braces for grouping and semicolons to terminate lines, although you'll notice that neither of those things appear in our grammar. They're mainly there just to make things more readable. Technically not in the grammar. Technically, they don't need to be. Yeah. Any questions about all that so far? Pardon me. Give me a thumbs up. So it's kind of funny to think of, like, if false then 0 else 1 as being a program, right? But, you know, a program is kind of anything that you define that, like, if you define a programming language, then there's no, you know, having defined the language is what defines what a program is or isn't. So even though this looks like a trivial expression, if, you know, it is a program in the language of UAE. So I have a question. If there's no semicolon, then how do you split statements? There are no statements. You don't need to split statements if you don't have any. This language does not define statements. It only defines expressions over Booleans and basically piano or arithmetic. Although, you know, the piano axioms are notably absent. So, note that, according to our grammar, we can construct a number of invalid programs, such as if 0 then 0 else 0, or successor of true, or is 0 false. Like, these are all perfectly valid programs in UAE, according to the grammatical specification. Our grammar alone is not sufficient to preclude this type of error. Remember, grammars do not describe semantics, only syntax. The above statements are equivalent to things in English, such as plastic orbits accrue Dakota portably. It's grammatically correct, but it's nonsense. In general, these are all examples of type errors, and this type of error is precisely the sort of thing we want our type systems that we're working up to be able to pick out ahead of time and exclude from compilation. Cool? Hopefully that's all cool. Let's see. So the next section is getting into like a whole another section. So we're gonna just leave that for now. I'll take any further questions that you might have, and then we'll close off this lecture. So here's a question for you guys. How is the course going so far? I know we've only really been covering, like, introductory material. But, yeah, Buffalo. Yes. I know we've only really been covering introductory material, but how does it seem so far? Also, here's a question. How does if false then 0 else 1 work again? Well, we don't really have to worry about how it works until we get to semantics. But, you know, it works in the same way as a regular if statement would. It selects either the then branch or the else branch based on whether the first term evaluates to true or false. Right? So if it's false, you take the else branch. So this evaluates to 1. If you want to know where the online tutorial will be, it's yeah, I think did I post that to the let me pull up Avenue. It's in the syllabus anyway. It should be in the announcement feed. Oops, I was supposed to hide my password. Now you know how many characters my password is. Yes, there we go. Virtual tutorial section. So it's Thursday at 10:30 for the virtual. Police, 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 police. Yes. So, could you... no, you couldn't define... No, Moonstar, you're not allowed to define binary syntax trees in such a manner that they have no branches and therefore conclude that there are no branches, like you don't have to choose one branch because there are no branches. I'm sorry, but no. You are expected to still have, you know, your proof can't be true equals true, I'm afraid. You're going to have to do a little better than that. So pred 0 would be invalid, right? Since this language doesn't define negative, so there's no predecessor to the constant 0. Well, it depends on how you want to define your semantics, really. Like if you're mapping things exclusively to the natural numbers, then you're right, absolutely. There's no negative natural number, it's just not in the set, so pred 0 would be a type error, right? However, you could just as easily say, with this syntax, we could just as easily map it to the integers rather than just to the natural numbers, since predecessor allows us access to the negative integers. So it really depends on... we're going to get into this a little bit when we talk about denotational semantics, but it depends on what domain of value you're trying to map your syntax into. So if you're mapping your syntax into natural numbers, you're absolutely right. And, you know, these slides so far have taken the position that we are implicitly mapping into this domain of natural numbers to give these expressions semantic values. However, since we have the predecessor function in there already, there's nothing preventing us from mapping it onto the integers instead. That would be a design consideration of the language. Cool. Is 0 is the predicate. Yes, so is 0 is a predicate over the set of numeric values, let's say, whether that's mapping to natural numbers or integers, we don't really care at this point, because if it's 0, then you get true. If it's not, you get false. It's going well. The assignment is a little tricky, but not too bad. The lectures are great. Okay, cool. Thank you very much. Launching brute force duel. For the virtual tutorial, was the link to the Teams channel posted somewhere? Yes, I posted it to... yes, that's correct, Grammar. I posted it to the Avenue announcements feed. For some reason, I wanted to say posted it, which isn't correct. Yes. Yeah, the Teams page. Also, I made the Teams page public, so if you just search for it, you should be able to find it. But yeah, okay, so A1 isn't too bad. Hopefully A2 won't be too bad either. That was kind of what I was going for with A1. It was like, it's like tricky but not too bad, you know? Like the idea, like I'm not trying to write assignments that are gonna like utterly crush you guys, you know? Because the thing is, when you're dealing with like such high-level formal mathematics, high-level rigorous mathematics, you can very easily crush undergraduates without realizing what you're doing. I have to be Atlas holding up the world for you guys. Or perhaps the Dutch boy with his finger in the dam. But yeah, okay. Well, I think that's everything for class today. Cool. I'll see you guys on Friday then. What's the due date of A2? Well, I gotta look at the syllabus for that. The reason I put things in the syllabus is so I don't have to remember them. What did I say? September 26th. Yeah, so assignment 1 will be due this Sunday midnight. Assignment 2 will be due next Sunday midnight. And as it, from the look of things, the rate we're progressing through topic 3, well, we're going to get bogged down when we start talking about this kind of stuff. But it looks like we're making pretty good time, so I need to get my ass moving on the topic 4 slides, eh? Get them out and released. So, good. Cool. Right. Take her easy, folks. I'll see you guys on Friday.